Our next presentation is RFFE, challenging the Wi-Fi Bluetooth status quo by unifying eFEM control. John Oakley of Intel. John is an RF control architect at Intel. He has over 20 years of successful digital design experience. He has 11 issued patents and has developed more than 55 successful integrated devices. He's an expert in 3 GPP standards and their application to real-world devices. John's currently the vice chairman of the MIPI RFFE working group and a member of the MIPI Reduced I/O working group and a member of the technical steering group. So, John?
Does this thing out? Does it work? Okay.
Yeah, it works.
Thank you. All right. Thank you.
Thanks, John.
Roy. Hi, everyone. All right, I'll have to figure out how to use this thing. It's my first time giving one here. And it says I have no notes. Okay, perfect. So the title, as you see here, is challenging the Wi-Fi Bluetooth status quo by unifying front-end module control. So that's what I'm talking about today is how do we move MIPI standards outside of the current mobile market. So, does this thing update? Okay, that one didn't update, but that one did. This one didn't update?
It should all update, yeah.
It didn't. All right, so we'll start with the, what's going on with that? But we'll start with the basic idea. Today, we're actually building Wi-Fi with basically individual components. We're starting to integrate these things into front-end modules. In the mobile market, we've been doing this for years, over a decade and for a lot of companies. So right now we're looking at how do we build Wi-Fi and Bluetooth devices that actually have more capability. How do we go to dual band? Because today on the market you'll see the 2.5 plus 5G modems that work simultaneously. And now I see myself, okay. All right, great. So, thank you. So basically now the question is how do we start building these higher and higher performances in our system? How do we integrate? How do we reduce costs? How do we improve performance? How do we improve reliability? So this is basically talking about, okay, how do I build a system and how do I look forward into what the next generation system will be? And so right now we'll talk about a little bit about why we're picking RFFE, why that's a good idea, and then why this is an improvement over the current system. So I'll just go to the next. So we'll start with the introduction. Today we're going to higher and higher data rates for Wi-Fi and Bluetooth. These are standards that we use in the mobile markets and the PC. And any connected device. You'll see a lot of IoT devices today using Wi-Fi. So we're integrating things into these front-end modules. Right now, most of them are using discrete IOs, as we say there. So these integrations, basically, we're doing this to reduce pin count, to improve reliability, to produce the ability to reproduce it, to make it the same and make it consistent. And so basically we're going to like a 2x2 MIMO dual band system. So we'll go here. We'll give you an example of what one might look like. An SoC today, as we show here, we're looking at a 2x2 system, which means we have 2 bands with 2 antennas. So we're looking at one device that may be, as I say here, chain A, the primary antenna with Bluetooth, and then we have a secondary antenna on a separate chain. And so how do we control the transmit and receive on these guys? And then we have, for 2 bands, that we build these things separately. As we go forward, we do more and more levels of integration. So today we're moving to this kind of topology. So you see a lot of the systems today are built like this. So the problem is, if you do anything else, we're looking at a lot, oops, back, sorry. Press the wrong button. That one updated, okay. All right, so we're looking at a lot of connections on this SoC. As we start adding features or adding control or adding anything, this basically becomes a hard thing to manage. So the example using our RFFE would actually had now combined all these guys into a common bus. And basically, you notice here the pin count reduction on the SoC went from having, I think it was 16 connections before, to basically 3 of these control connections, just plus into the tech lines. This is kind of how we're building the system today. This actually allows us for more flexibility. We can do basically control more devices. If you controlled 1, 2, 3, 4, however many antennas you wanted, if you wanted to build a 4x4 MIMO system, we could still build it the same way from the SoC, but then actually have that kind of flexibility. So this kind of reduces that control from 3 per device to, or 3 or 4 per device to just 3 from the SoC. You'll look at the actual FM devices, the front-end modules are still kind of the same kind of connections. Integrating these in together is kind of another ongoing task that's going on, but that's kind of outside of the scope of the discussion we're having today. Right now, we'll just talk about what we can do on the SoC side, what we can do for this interconnect side. So, next one. So, a couple examples of what these are devices would look like. Basically, it's a switch, an LNA, basically a straight through pass for high energy levels, or basically when we're close to the source, and then basically selectable PA or bypass. So this would basically be a common example of what a front-end module might look like. Now, so we actually have a couple system states that we're talking about today. What would this discrete signaling look like? We basically have a standby state, a transmit state, a gain state where we're far away, a bypass state where we're close, and then maybe Bluetooth. So these are different configurations we'd have for our front-end module. For these high bands, since Bluetooth is only the 2.5 gig, it's not included here. So this kind of gives an example of what this might look like as a system. Relatively simple, but these are kind of the standard states you might see in these connected Wi-Fi Bluetooth devices. So I guess I can move on. So it's kind of getting a little bit more complicated to see, but when we move to this standard connection that we show, we're gonna move back here. When you move to the it's integrated system, we now have to think about how we control this, because control is always the question that we come. How do we combine all of these different states that we could have controlled individually with GPIOs? How do we kind of unify that into a single system? So this is kind of an example of what this might look like from a system mode, where we have here basically system modes where everything's off. Okay, we're in airplane mode. We could be transmitting, we could be basically a combination of bypass versus gain, depending on whether or not you're doing high band or low band. So you know, for all the connections are now shown here. We could be running Bluetooth on one and maybe Wi-Fi on the other, right? So all these things are all possible type configuration modes. Here's kind of what you'd see in an existing system today. So basically the idea here would be we could put all of the enables and disables. RFFE has these standard registers. So RFFE is based off of communication protocol where we do accesses to various devices. So register is basically a place where we can store things and control. So register 1, I'm saying we can put all the enables and disables here. And what we do here on register 0 is basically with a pointer that would select which system mode you would want. If we do this, now I can quickly switch between system modes with a single write and change all the devices. Since we're all on a common bus, I could either change one individually, change them all at the same time. I have flexibility. And flexibility allows us to basically handle all these different use cases, handle it in a controlled way, handle it in a holistic manner, because that's kind of how we have to build a system. So, just kind of an idea. So, kind of a simplified control interface. So, flow diagrams always kind of help explain some things. But basically, we would start, we'd power up the part, we'd wait for configuration, we'd go to a new mode, and we'd go back to idle. So, try to keep something pretty simple from a control perspective. The way we would actually update a mode would basically be either switching that register 0, which basically says what system mode are we going to. Is it a receive, a transmit? Am I doing Bluetooth? Am I doing Wi-Fi? Do I have to add gain or not add gain? So basically, maybe I have to turn off or on a certain operation. Maybe I only want to do 1 band or 2 bands, or maybe I have to do both. So all of that is possible, and we can do kind of a simple control flow and simple control paradigm. We can expand this to a 3x3, or I know you wouldn't really do a 3x3 front end, you would do a 4x4 front end. But you can expand this to anything you want. You could add more bands, you could add different levels of integration. Maybe you could integrate the high band and low bands together, which we see a lot happening in the mobile market, not so much yet in the PC market. But all of these things are possible with a similar kind of control structure. So we'll kind of go over some advantages. I know I'm going through this quickly, but why would we use RFFE? Basically allows us to use a reduced pin count. As we add features and complexity, this gives us a way of moving forward. Adding more pins basically is expensive on an SoC. SoCs, every time you put down a pin, you basically have to route to it. You have to make the device bigger. You have to control it. I mean, all of these things are just cost and make things not very expandable. So that's one of the advantages here is RFFE gives you kind of a unified method and you find a control thing. And then we could basically carefully specify, I know I'm talking about some things using RFFE. What is a broadcast right, as a term I use here? Broadcast right is a right to everyone. The RFFE has all these devices on there. You can either be uniquely identified or they can be broadcast. That means I talk to everyone at once. So then I could say some things I could do, right to talk to all the devices, switch them all at once. With this GPIO-based approach, usually every device from a software perspective is handled independently. So that means I have to run one piece of software to set up one mode, then the next mode, the next mode, next mode. By unifying this into a common control scheme, then we could do this all at the same time, at the same way. This common control mechanisms, we control things simultaneously. So doing one RFFE write to talk to all the devices. Or if I want to continue the old way, I could write to one device. So one thing, RFFE is normally pull down to ground and use the slew rate control. One of the things this does do is this also helps me isolate the SoC from the front end. Because the SoCs can be noisy, the power supplies in SoCs can be noisy is I guess the best word I can use. So by actually helping create that isolation, keeping everything at ground, actually keeps the noise to the front end that would come from this main SoC minimized. So, which is quite a helpful thing, especially when you look about some of these Wi-Fi devices as we try to get, I want to get 200 meters or whatever, I want to go further away. How do I make that happen? So this is one of the things that you can actually leverage to move forward. More advantages. I can do more control options. One of the advantages, now that I have a common control mechanism where I can do reads and writes, I can basically do new features. I can basically say, okay, I put a temperature sensor out there. I measured how warm it got. Maybe I do other things. Maybe I say, I added a blinky light. Who knows, right? These are all things that can be added to a system with minimal change to the way we control, the way we use it, and all that is all now kind of in the same ballpark. So this is kind of one of those nice things about building a system like this, is I can now add or remove features. I can know high-end parts, low-end parts are all kind of the same from a control and from the SoC standpoint. It actually allows for the possibility of reading. So if you think about that original design we looked at, everything was basically control. I just said turn off or on. I enabled or disabled features. Now that I can now read it. Maybe, as I said, that temperature sensor I put on there, I now can read it. Or I could say maybe my power level is too low for a given state and I can adjust power. So all these things allow for me to increase the reliability, increase debug, increase performance and features of a system. One more advantage here, there are billions of devices that use RFFE today. MIPI RFFE actually is in pretty much every phone that is made today. I'm not sure if it's all of them, but it's definitely a very, very large percentage. Each phone uses 10, 15 of these devices. So we're looking at hundreds of millions of these devices produced a year. We have a large infrastructure of people using it, large team talking about it, trying to make sure the standard is clean and that people's needs are met and that we're able to move forward. So having this kind of collaborative effort that MIPI basically brings to the table basically can be utilized in other things like Wi-Fi, Bluetooth, basically for the laptops, for industrial, for IoT, for all these other features can all be done. And if you want more, I know I kind of condensed a paper I'd written about this down to these slides, and it looks like I'm kind of blowing through my time. But so the white paper we have here, so we've now uploaded it to this MIPI site, and it's one of those things. I'll just say this: MIPI gives us this framework and this interconnect and this way of talking and this agreements, and that allows us to basically make systems better and cheaper and moving on. And we're integrating devices, and now we can integrate a device, we can integrate multiple devices and not have to change how we control it. And then we could add new features, remove features, all that stuff can be in the same kind of control game. So that's actually what we're trying to say, and this is just an idea that we'd like people to pursue, and I guess that's question time. Only 15 minutes, but I mean, you have questions about this? I know we kind of went through a high level. I don't have any pretty PCB pictures like everyone else has, but trying to think about how we build things, how we move beyond where we are today.
Any questions for John?
Wow, easy.
You wowed us. We're speechless now.
Yeah, maybe too fast.
Just a tad.
Yeah, okay, probably.
John.
We do have a question here.
Oh, yay!
Yay.
Awesome.
So, John, could you please give some highlights, like what is the upcoming plan in terms of, let's say, meeting the RFFE needs at higher speed? What is your plan there in that space?
Okay, so kind of a little off topic, but that's fine. So one of the things about going to a common control mechanism, it's a 3-wire interface as we saw. So I'll go back and I can talk to the slide here real quick. So as he says, one of the things that we talk about here is MIPI has a speed of nominally 26 megahertz. We've, in the 2.0 spec, we actually expanded it to support 52. Now the question is, how do I get beyond that level? What can I do to basically get more control, faster control? There are definitely discussions with the groups among all the companies that are involved. And we have a wide selection of companies from the slave side, from the manufacturer side, or from the master side. Master being the one that controls, the slave the one that listens. So these are ongoing discussions. Now, how do we go faster than this 52? I mean, as our esteemed colleague has asked, we are actually looking at other ways of potentially going beyond what we have today. They're still under discussion, so none of them have been finalized yet. When they are, we'll definitely agree to it as a group and move them into the spec. A lot of the things that we look at now is how do we improve the way that we actually talk between these devices? How do I add features without basically breaking the backwards compatibility with these slave devices? Because with a history that we have of 10 plus years on some of these devices or some of these companies, adding new features may be difficult. So maybe I pick up a device that is brand new. Maybe I pick up a device that's 10 years old, and I want them to all interwork together. So these are kind of the frameworks and the questions we ask, and we try to make sure that the standard moves forward and supports all of these things together. I mean, it's a good question. It's hard for me to answer right now. I can give you kind of the framework of the answer, right?
Yes, sure, thanks.
Any more? Love to talk about RFFE. RF front-end control. It's good topics. All right. Thank you.
All right. Thanks, John.
Thanks. Too fast.